Okay, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everybody. How's everybody doing today? Yeah, that's right, Taco Tuesday. You can always make your own tacos. Yeah, among many things, I've been getting into cooking a lot. So cooking is one thing I've always enjoyed doing for a long time. So I've gotten the chance to cook a lot more. I usually don't get that many opportunities because my girlfriend really likes to eat out a lot. So a lot of times, I'll cook something and she'll like it after I cook it, but then then later she'll want to go out. But now that we're forced to stay home, that you know I've been cooking a lot more, so it's been fun. Okay, so the plan for today is we're going to do ANSYS activity 6. So this is our final ANSYS activity. So this is in favor of the final presentation. So kind of if we were sticking to the original schedule, this is when we do presentations. But the people voted, and the people voted to do more ANSYS stuff. So that's what we're going to do. So we're going to do ANSYS activity 6 today, which is going to be on topology optimization. So this is a feature that someone in the class actually looked into beforehand that I didn't really know much about. So it's actually after he showed me kind of what he was doing with this, I looked into it myself, and I thought this would be something cool for everyone to learn. So that's kind of where this activity came from. Okay. So the plan is I'm going to start with just a short lecture just to talk about just what optimization is and how that can be applied how that applies to ANSYS, because optimization in itself is a really large and really diverse field that spans very, very many disciplines. So actually it has its roots in kind of applied mathematics. So we won't go into the details of behind the scenes, but I think it's good just to know a little bit of background information, what optimization is and what it aims to do. Okay? I have another announcement too, that I got an email just now that said that the SOQs for this semester are online. So those are going to be available to you guys on the student portal. So according to the email, once you guys log into your student portal, there's going to be, it's going to be very clear, how you apply those SOQs. So I can't log in as a student, so I can't see it. But according to the email, it's very obvious. And apparently they're going to keep sending you annoying emails until you actually complete it. So I think that would be something good to do, because normally we do those in class, but obviously now that we don't have any class sessions anymore, that we're transitioning to an online SOQ. Okay. So just a few words on the SOQs. Please fill them out. Especially you should fill them out for all your classes, but please at least fill them out for mine, and please be as honest as you can with those feedback, because throughout this entire semester, you guys have I've been giving you guys a lot of feedback on just finite elements, but kind of just as you guys are learning finite elements, I'm still kind of learning how to teach kind of the best way that I can. And one of the best resources that I have in order to improve my own methods and get better at what I do is the feedback from you guys that that I get every semester. So I look at all the SOQs, I read all the comments, good and bad. So and I always try to take those as best as I can and try to apply those forward. So that feedback is really important to me. So please please fill them out, and please be as detailed as you can with that feedback, because anything that you guys can say, I think will only kind of help me at the end. Okay? So please definitely fill those out, and please be honest. That's kind of okay. Okay. Are there any questions about anything before we get started today? Right. So the question is, how do we view feedback from the project? So yeah, that's right. So yesterday I gave everyone feedback on their progress report. So so everyone seems like everyone's project's coming along really well. So that was really good to see. So if you go back to the assignment page on Titanium, basically the same place where you turned it in, and you click that assignment, you should be able to see my feedback there. But I think for most people, I try to remember to click this, but when I was done typing my feedback, I clicked the check mark for notify student, and that hopefully that did send you an email. So hopefully most people got an email with the feedback that I gave, but if not, or if it got lost somewhere, then you can always go back to Titanium and check it from there. But if you're having trouble viewing that, oh, it shows on your grade section too. But if you're having trouble viewing it, then just let me know, and I can send you the feedback kind of directly to you, just like that. Right. Okay. I also I got a question yesterday about the previous activity, because I know the last activity was a little bit more lengthy than the previous ones, especially with all the clicking. And for those of you who are working on the virtual machine, because it's really slow, it was kind of really difficult to finish that assignment. So what I've been telling people is that for the rest of this semester, and this is going to apply to everyone, because of the difficulties that we're having with especially with us just getting access to ANSYS. I'm going to be waiving any late penalties for the rest of the semester. So I'm more concerned that you guys are just doing the activities and you're learning the skills and ANSYS. So please just get it in whenever you can, sometime before I have to submit grades. It's kind of hard after I submit grades, to go back and change it. So if as long as you finish the assignment at some point in this semester, and you notify me, then I can give you credit for it. Okay. Just because with the way things are, and I know you guys are really busy right now. I heard they dropped a bombshell on you guys for that virtual ECS showcase this Friday. So I know a lot of you guys are gonna be busy with that as well. So with that in mind, I want to waive all late fees, for the or late, not fees. I'm not charging all late penalties for the rest of the semester. So for ANSYS it could be 5, 6. Please don't try to do it for the project. Yeah. Please try to be on time for the final project report, because I have to. That is something I have to look really carefully about for the rest of this. Before I submit grades, but I'll give you some wiggle room on that too. But just try to get everything in before the end of the semester, and at least give me 48 hours to grade everything, and we should be good. Okay. All right. Any final questions on just logistical stuff, or anything before we get started with the activity? Okay, so let's go ahead and get started. So today we're doing ANSYS activity 6, our last activity. So in this activity, we're going to be going over a feature in ANSYS called Topology Optimization. Oh. Okay. And so the kind of the word that I kind of want to focus on in this title is optimization. Okay? So optimization and computer simulation, they kind of go hand in hand. So optimization, kind of as the name implies, it's a way to take a situation that's maybe not working as well as you want, or it might be inefficient, and trying to make it as good as you can. Okay, that's kind of as general as a way that I can call optimization. So optimization is a way, I should say a systematic way of improving a problem. So I have a little bit of background in optimization, just because my next door, or my lab mate, the one that kind of sat next to me in grad school, he was a really big expert on optimization. So just by sitting next to him, just by kind of osmosis, I kind of absorbed some of his stuff. So I'll kind of say this, that in reality, the kind of the world of optimization is a field that's very, very deep. I would say probably even more deep than the field of finite elements, because it's something that can be applied to so many different things. So we'll be applying it in terms of finite elements and design in particular, but optimization kind of has its roots in applied mathematics, which you can imagine is a huge field, because engineering is kind of just a small sector of the field of applied mathematics. So that's kind of the definition that we're going with. So just kind of a way to make it better, right? And it's, you know, kind of the big thing that I want to focus on is that when you're doing optimization problems, you're not looking for a single solution, right? Because usually when we do engineering problems, like say, you know, you're solving a problem in fluid mechanics or maybe a math class, you find kind of a single answer to your problem. Okay. So just as an example, okay, a very simple example, we know that 2 plus 2 is equal to 4, right? Allegedly. And because of the rules of mathematics, we know that 4 is the only answer and this is the best answer. So even, you know, um, even, you know, if we compare it to kind of the problems that we were doing it just in this class at the beginning of the semester, when I asked you to solve for like the strong form solution of the problem, the weak form, there was one solution to that problem, right? But in reality, you know, if you look at a lot of engineering problems, or even just, you know, other stuff too, there's never just one answer. So for example, so, you know, we have 41 people in this lecture right now. So if I ask, you know, all of you guys what the best movie in existence was, I guarantee you we'll probably get 41 different answers. So there's, you know, there is no kind of formula you know, to determine what the best movie is. Like everyone kind of has their own preference and everyone kind of has their favorite movie, but, you know, it's hard to tell, you know, what the absolute best movie is. Of course, you know, that we can always discuss that and argue that. But you know, that would be, you know, we'd get nowhere. Right? So a lot of engineering problems are kind of the same way. So for those of you guys who are doing senior design, you know that, you know, probably what happened was you were presented with a certain problem or certain objectives that you were trying to accomplish through your engineering design. And as you kind of went through the process of trying to, you know, develop a, you know, whatever your engineering system, you know, you saw that there's kind of you know, an infinite number of ways that you can accomplish those objectives within those constraints, right? And that's kind of you know, why optimization and kind of engineering kind of go hand in hand, because it kind of helps to find, you know, kind of helps you explore that kind of infinite space. So even though there are many solutions to the problems that you've been given, there are definitely some solutions that are better than other solutions, right? And that's kind of what optimization hopes to do. Okay. So for example, you know, if we, for this activity, what I'm going to do, or what I'm going to give you is a CAD model for a wall bracket. So this wall bracket is basically going to be responsible for holding up a certain amount of force. Okay? So, you know, if we look at the wall bracket and we look at the, you know, the stresses that develop inside it, you should see that it's in no danger of breaking. So the wall bracket that we have definitely fulfills its role, and it's perfectly serviceable. You know, but that kind of, you know, but because this activity is an optimization activity, we have to ask, like, is there kind of a better bracket, or is there kind of a better way to kind of satisfy these constraints, you know, and kind of save us some material. So in this case, you know, what we're going to do is we're going to ask ANSYS to basically find us a more efficient bracket that kind of satisfies the same goals, but, you know, with less math. So it's going to be cheaper to make, basically. Okay, so how do optimization algorithms work? So the way optimization algorithms work, um, it's a bit different from kind of our normal solution protocol, because normally when you solve a solution, you kind of follow a kind of a recipe of steps, right? Okay. So if we're talking like the strong form of a problem, the recipe that we followed was we took our differential equation, we integrated it twice, and then we applied the boundary conditions and we solved for the constants, right? But it's kind of a very clear-cut recipe. So for optimization problems, because we don't know what the best solution looks like, there really isn't a recipe that we can follow and where we're guaranteed to get something good at the end of it. Okay? So the way I kind of like to think of optimization algorithms, and so for optimization purists out there, they might get mad at me at this, but the way that a lot of them work is basically like an educated guess and check. Okay. It's not as random as I'm kind of making it sound, because it's not like the algorithm is going to just guess something completely random and then just check the solution. Um, because so it's a lot more nuanced than that. So the guess that it does give you have some kind of rhyme or reason, but what you'll see kind of as we run it in ANSYS is that kind of the solution kind of builds kind of incrementally, where we're going to start with some initial state. Okay. So in our case, the initial state is going to be our original CAD file. Okay. Then once the optimization starts, what ANSYS is going to do is going to propose kind of new solutions. Kind of based on its kind of educated guess and check, or that's the guess step. Okay. Okay. And then after it proposes a solution, what it's going to do is going to check it. It's going to check. Is kind of our new guess, is that kind of better than where we were before, based on some metrics that we can specify. So if it is, then we can save it. But if not, then we just throw it away. We say that was kind of a bad guess. We'll kind of forget that ever happened. Okay. And then this kind of repeats over and over again. Okay. So once you have your initial state, and you start proposing solutions, you kind of enter into this loop of like propose new solution, check it. Is it better? And then propose a new one, check. Propose a new one, check. So over time, eventually, through all this guessing and checking, you're going to arrive at something that's hopefully better than what you started. Okay. And so just a little bit of terminology. So each kind of cycle of proposing a new solution and checking, this is what's called an iteration of the optimization. Okay? And so that term will be important, because that's that's one kind of parameter that we need to set within ANSYS. So it's kind of important to know what an iteration means for an optimization algorithm. Okay. Any questions on that? Right. So the question is, so this will propose a new geometry to our CAD model. Yes. Yeah. So what ANSYS is going to do is going to propose a better geometry for your CAD model that will be better according to its taste. Unfortunately, the model that comes out is it's not going to be a clean model, so it's going to be kind of rough. But it should give you some ideas on how you can improve the model. So what I'm going to recommend is that generative design. I've not heard that term before, but I'll let you guys decide if it's the same thing. So what's going to result? What's going to result from ANSYS is that we're going to get an optimized model, but it's going to be pretty rough around the edges because it's this is basically being done by a computer with kind of no knowledge of how easy or not this is going to manufacture. But so what I'm going to recommend is that you kind of take kind of the general result that you see and then use that as kind of information to kind of modify your CAD model kind of post kind of manually. You'll see it'll kind of make sense once we get there. All right, any more questions on this? Okay, so one more thing that I want to cover. So let's go over this guess step, okay, or the check step. Okay. So for every optimization algorithm that you see out there, including the one in ANSYS, but also kind of more generally, if you're interested, actually, MATLAB has a lot of really great optimization algorithms too. The one thing that you always need for an optimization algorithm is what's called a cost function. So you can think of a cost function as kind of a way for the optimizer to grade those geometries. Okay? So if you think of the final project, I've given you guys a rubric on how I'm going to grade your final projects. So the cost function kind of serves the same function. So what the cost function is going to do is it's going to take certain characteristics of your engineering system. So some things like mass, the maximum stress, the volume, stuff like that. So it's gonna take all of these parameters into account, and it's gonna give you kind of a single numerical score that kind of tells how good this guess is. Okay. So I actually don't know the exact cost function that's inside ANSYS, but if I could kind of make one up, this is something that I would do. Okay. So one thing that we're going to optimize for in ANSYS is that we're going to optimize for the mass. So basically what we want is we want basically a new geometry that can satisfy all the loads and constraints without breaking, but with significantly less mass. Because what we say is that if we can come up with a different wall bracket that still satisfies the loads, but has much less mass, then this is going to save us a ton of money on materials because we can manufacture this part with much less money. Okay? So an example cost function for this could be something like 1 over mass. Okay? And usually for this case, mass is always going to be positive, but generally what you'll see for cost functions that you'll see kind of in the wild is that you kind of have this squared and you square root it. And the reason for this is that this is just a guarantee that it's a positive number. Okay. So another way, of course, you can do this is you can just take the absolute value. So that's another way you can do it. But if you have kind of multiple factors that go into your cost function, here we just have one, so we just have the mass. Then you would apply kind of a squared. You would square each one, you would add them up, and then you take the square root of the whole thing just to make sure that they're all positive. Okay. And so basically, with this cost function, we can say that if we have a geometry which has more mass, it's going to score lower because we have 1 over mass here. But if we have if we compare that to a geometry that has less mass, it's going to have a higher cost function value. So using that formula, then the optimizer knows that this geometry with less mass is more desirable. So then this is one that they can do. Okay. So in this case, we only have one metric, but this can combine a lot of other stuff. So and I know in ANSYS they do a lot of a lot of different objectives. Right. So the question is, it's a lot of times it's kind of hard to know how many iterations that you need to run the optimization. So like Chris was saying, kind of a lot of times your limiting factor is going to be time. So we're doing a relatively simple case here, but for some more complicated ones, it takes quite a long time to actually run an optimization algorithm. So you can kind of set your number of iterations based on that. Yeah, so our optimization will kind of run in the matter of minutes, but I know some of the stuff that my lab mate was working on, and some of the smaller optimizations that I've done too, they could run for days. So a lot of times there's kind of a big difference there. So obviously you can set more iterations to be more accurate, but you can also lessen it if you kind of need the results faster. But we'll kind of cross that bridge once we set those settings in ANSYS. All right, any final questions on this before we jump into ANSYS? Okay, so let me share my laptop screen. That's fluid. So I'm working on the fluid mechanics activity for next week. Okay, so our starting point is going to be ANSYS Workbench, just like it always is. Okay. And so what we're going to do is first thing we need to do is we need to create a CFD sucks. CFD is cool, but it is hard to set up. Yeah, we'll go over that next week. Okay, so first thing we need to do is we need to kind of form a base for the optimization. So you can see that we have topology optimization here in the toolbox, but topology optimization, you need some kind of input to, in order for it to work. So for this case, we're going to use static structural. So let's start with the static structural here. Okay. So just like before. And then let's import a geometry. So I've uploaded the wall bracket that we're going to use for this simulation. Okay, so it's been a while. So let me browse for it. So if you download the geometry, it should be wall bracket for optimization or something like that. Let's see. ANSYS files. Yeah. So the file is called wall bracket for optimization. So I created this model in Design Modeler, so it's an ANSYS type file. So hopefully there won't be any issues in importing it in. Okay. And so once you've imported geometry, we can go ahead and double-click Model to open up ANSYS Mechanical. So if you're kind of following along in the PDF, we're doing problem 1 right now, where we're setting up basically the static structural simulation. So before we actually jump into the optimizer, we actually need to run a simulation before that, because the optimizer needs to know what are going to be the loads and constraints that are going to be applied on this model. Okay? And the way we're going to do that is in static structure. Okay, so here's our wall bracket. Right? So it's a nice square piece of geometry with fillets there. Okay. All right. So first thing we're going to do apply our mesh. Okay. So in this case, you know, and traditionally you would, you know, apply all those different objects there. But in this case, I'm just going to set a kind of a standard mesh. So in the kind of just in this mesh tab right here, we can set the element size here to be 20 millimeters. So let's make sure we're in millimeters here. Okay. Was 20 there. Let's go ahead and generate the mesh. Okay. So this gives us a pretty decent mesh right here. So the we can check the number of elements. So we're at about 4,000 elements. So that's pretty good. Okay. Right. So you can for your own computers, you can make this more fine or more coarse if you want. But 20 is kind of a good midpoint. That's kind of what I set this. Okay. And kind of most importantly, I set it such that you know, we kind of have multiple elements through the thickness here. Because you remember from ANSYS Activity 5, you know, in order to compute stresses accurately, you want to have at least, you know, ideally you want 3 elements through the thickness, but 2 is much better than 1. So we have 2 elements through the thickness here, so we're usually good to go. Okay, so now let's apply boundary conditions. So first, let's do a fixed support. So let's go right-click static structural here and do fixed support. Okay. And so we're going to fix these at all of these holes right here. So we'll go ahead and select all 4 of these holes. Okay. So this is going to model the effect of this wall bracket just being fixed to the wall. Okay. So that's right there. Okay. And then we're also going to add a force, a downward force. So we're going to right-click static structural, insert a force. Okay. And then we're going to apply a downward force on these holes right here. So let's go ahead and select these holes, the surface of the holes right here. So if it helps, click surface mode right here. So click that hole, click this hole. Okay. So let's go ahead and apply. And then let's define this by components. And then let's define a force in the minus z direction. So we'll do minus, I think we'll do 10,000. Okay. So minus 10 kilonewtons. Okay. Right. And so before we run the simulation, let's get our result field. So let's say that we want total deformation. And we also want stress. Let's get equivalent von Mises stress. Okay. So now we have the mesh. Now we have the boundary condition. So we can go ahead and hit solve. Right. So since we had a relatively coarse mesh, we're already done solving, so we can check the results. Oh, I guess we're not done solving. Okay. Come on, ANSYS. It should be on both holes. Yeah, so in the picture, it looks like the arrow's just on one of the holes, but I actually selected both. So if you look at kind of the figure in the PDF, both the holes are kind of highlighted in red. So we want to apply the force on both the holes. Yeah, so after this is done, I'll show you guys the support again. Okay. Oh, did I only select one of the holes? Oh, okay. I only selected one of the holes. So it should be both. I think I forgot to select control. Thank you. Right, so we've so apply the force on both the holes so that they're kind of symmetric like that. So you guys want to see the support again. Okay. So let me delete this and edit again. So we have a fixed support. Okay. And so for the fixed support, we're gonna fix it at all these holes right here. So the 4 holes in the back. Because what we're saying is that the wall bracket is basically going to attach to the wall at these holes. So we're going to select these faces. So make sure you're on face select mode. So go ahead and click this hole. Hold down control, click this hole, and then click this hole right here. Okay. So you should have all 4 holes in the back selected for the fixed constraint. And then once you have all 4, you can hit apply. Okay. And so now we fixed at those surfaces. Our force should be on both of these, which is kind of hard to see with the mesh on top. But hopefully I see a little tinge of red right here, so that's good. So let's go ahead and hit solve again. My laptop might be a bit slow because I'm running the CFD code and also this instance of ANSYS at the same time. Okay, so this looks good. So after you apply the boundary conditions, you should get a deformation field that looks like this. And so because we applied the forces at these two end holes, we have a large deformation here. We have a deformation of 0.446 millimeters. Okay. And then if you look at the equivalent stress field, you should see something like this, where the stress is kind of maximum up here where the bracket attaches to the wall. Okay. Okay, so was everyone able to get this this result field for the deformation and the stresses? Okay. And so before we move on to the optimization, I kind of want to point some things out here on the equivalent stress field. So if you're up to this point, you can click on equivalent stress, and you can look at the field. Okay. So what I want you to notice is that there's a lot of portions in this field where the stress is almost it's much lower. Okay. So we have for the regions that are dark blue, we have a stress that's 0.087 megapascals. Okay. So if you compare this to the regions where the stress is high, we have kind of a almost like a 4 orders of magnitude difference here. So we have 31 here and then 0.087. Okay. And so what the dark blue is saying is that these regions with very little stress are doing very little in terms of load bearing. So they're basically kind of sitting there, but they're not really doing any work on kind of helping to support the load. So it would be kind of nice if we can kind of know which areas we can cut out, which aren't really doing much, to kind of to satisfy the same constraints and loads, but kind of save us some material costs. There's a question. Yeah, my laptop is it's a gaming laptop, so it can handle quite a bit, but it's yeah, it's difficult. Okay, any questions on this before we exit out of here? Okay. So then now that we've run our static structural simulation, we can go ahead and exit out. Okay. So that should take you kind of back to the workbench. Okay. And now what we need to do is we need to initiate our topology optimization. So on the left-hand side right here on the toolbox, you should see topology optimization. And so what we're going to do is we're going to click and drag this into our area, but we're going to drag it onto I think the results section, right? Yes, okay. Or the solution here, okay? So this is important. So when you drag your topology optimization out here, you don't want to create a standalone system. You want to link it to your static structure, okay? So in order to do that, you need to drag it on top of your solution right here, okay? And so if you do that properly, you should see, a new box show up here, and then you should see some links, okay? Right? And so once we do that, we can double-click Model, which will open up topology optimization again. Actually, double-click Setup. Okay. Basically, you want to double-click the one that has the refresh sign. Okay. So it's going to take a little bit of time because it's kind of loading two things at once. So it's kind of it's loading the settings from our static structural, but also loading in new stuff for the topology optimization. Okay. So after we do that, you can see we're back in mechanical. So you can see up here we have our static structural A5. So all of this is still the same as before, but now we've added this new section here for topology optimization. Okay. And so what we're going to do is we're going to kind of walk through each of these kind of one by one and kind of talk about how we can set these and kind of what the significance of each section is. Okay. So the first thing we're going to do is we're going to start with analysis settings. So underneath topology optimization V5, let's left click analysis settings. Okay. So in here, we can set a lot of settings for the optimization itself. Okay. So the first thing that I want to draw your attention to here is this first setting right here called the number of iterations, right? So remember when we talked about earlier in the class today that an optimization algorithm is essentially going to be a guess and check. So you basically need to put a limitation on how many times you can guess and check, right? Because in theory, with the guess and check approach, and not really knowing what the absolute best solution is, you could guess and check for an infinite amount of time, until, you just grow tired of it. But a lot of times, we ain't got time to let the computer basically guess and check until it's satisfied. So a lot of times we need to put a cap on how many iterations that it can run. Okay. So here the default number is 500. So for now that one's okay, just because this model was relatively cheap. So we only had about 7,000 elements here. But if you're running a topology optimization on a model with, say that we're running this up to the student limit, so we run it up to 32,000 elements, or even, if you use this in practice for a model with like hundreds of thousands or millions of elements, you're not going to want to run the optimization 500 times. So you might want to limit this even more. Okay? But as you can imagine, the more iterations that you give it, the better solution that you're going to get in the end. Okay, so this is kind of a setting that you can play with to kind of, play with the kind of the cost versus kind of benefit. So the more iterations gives you a better solution, but takes longer. But you can set this lower if you want kind of results faster. Okay. Oh wow. Yeah. So Chris is saying that for something that reached 500 iterations, it took them about 75 minutes. So yeah, you definitely want to be careful with this setting here. And so the other thing that you can look at here is this setting right here, convergence accuracy. Okay? So throughout the optimization and through its guess and check, what the optimizer is going to do is it's going to check, every time it finds a better solution, it's going to see how different that better solution was from the previous one. Okay? Because often what can happen sometimes is that the optimizer will keep finding new better solutions, but they're only just a tiny bit better than the previous one. And that can happen a lot, especially for cases where you have a complicated cost function. You might only be making just very, very incremental improvements over the previous one. Okay. So in those cases, you don't really want the optimizer to work, for another, 2 hours just to find something that's only like a 0.01% improvement over the last one. So if you, what you can do is you can say that, okay, once the improvements kind of reach kind of this kind of minimum threshold, then we can kind of stop and we can say that this is kind of the best that we can do, right? So that's what you can set here for the convergence accuracy. So what this is saying is that once the new solutions are only 0.1% better than the previous ones, then the optimizer will kind of kick itself out and say that, this is kind of the best that we can do. Ah, I see. Right, so Sam was saying there's a few softwares dedicated to this, and most of them offer cloud computing. Yeah, because the minimum specs is 12 core processors. Yeah, that sounds about right to me. Yeah, because optimization, especially for expensive models, is you need kind of multiple cores in order to do it correctly. Yeah. Mm-hmm. All right, any questions on this? Okay. And so the next thing that we can set is the optimization region. Okay. So this is going to be something that's unique to ANSYS. So basically what's going to happen is that the optimizer is going to basically cut out some mass from this wall bracket to make it better. Okay. But what we can do is we can tell ANSYS to only cut mass from certain areas. Okay. So after I click this optimization region, you can see certain parts of the model, some of it highlighted in blue and some of it highlighted in red. Okay. So the blue portions are going to be the ones which we call our design region. Okay. So the design region is going to be the regions of our model where we're say, it's okay for ANSYS to remove material. Okay. So basically, this is the area that we're letting ANSYS design for us. Okay. So in this case, the majority of the wall bracket is highlighted in blue. So we can say that, wherever you feel like in the blue area, you can just take out material and we're okay with that. Okay. And so the other thing that you can do is you can set what's called exclusion regions, where you can tell ANSYS that these are kind of regions of the model where, I don't want you to take stuff out. So this is kind of either geometry that you want to keep, just because it's easy to manufacture, or, it might be that, if you're bringing in a CAD model of and part of it's like a commercial part that you can't really change all that much, you can tell ANSYS that this part of my model is kind of a commercial part. I can't really do anything about it. So don't include it in the optimization. Just exclude it. Okay. So one thing that ANSYS will do by default is that anywhere that you applied a boundary condition or basically a constraint or a load, then it's going to automatically exclude those from the simulation, because these are areas where you're either going to attach something, or those are areas where it's going to be load bearing. So you don't really want to take those away from your optimization. Otherwise, it's going to dramatically affect the model. Okay? So in this case, we applied boundary conditions on all of our holes. So if you remember from the holes on the back, we applied a fixed support. Okay. So we've excluded those from the optimization. And then from the two holes on the front, we've applied our weight load here. So we've also excluded those from the optimization. But everything else is basically fair game in the optimizer. Okay. Any questions on that? Okay. So let's go down the line. So next we have objective. Okay. So once you click objective, then the window is going to change. So now we have this menu right here. Okay. So remember, like I said before, that optimization algorithms always work with some kind of objective function. Okay. So basically, this is how you can define the objective function for this topology optimization. Okay. So I haven't really had a chance to play around with this all too much. But I'm sure there's a lot of online resources where you can do to kind of change these settings. Okay? So right now we only have one objective, and that's basically to minimize the kind of the mass here. Okay? But you can actually add more objectives here too. So you can actually right-click here and add more objectives. So you can kind of do a multi-objective optimization. Okay? And it's really in those optimizations where you add 3 or 4 or 5 objectives. That's when the optimization algorithm really tends to shine. So, the example that we're doing today, it's going to be a little bit obvious what the optimized solution is, just because we only have one objective. But for a part that's more complicated, you can add more objectives here, and you can and the optimizer will really begin to shine, because it's for kind of when you have 2 or 3 or 4 or 5 objectives, it's kind of really hard for kind of the human brain to kind of process, how to change that, because oftentimes when you're optimizing for one objective, it kind of makes another one worse. So in order for you to kind of keep track of everything, a computer is really good at that. So that's what this is here. So for now, we're just going to leave this on the defaults, but this is here for you if you want to kind of do more multi-objective optimization. Okay. And so the last thing that we'll set is the response constraint. So in addition to the objective function, the other thing that you have to set is the constraints of the optimization. Okay? Because what we said was that the optimizer is basically going to be doing a bunch of guess and check, but there's some limitations on what we want to guess and check. Okay? So constraints on optimization, they kind of take a lot of different forms, but for this case, since we're doing an optimization on the mass, we can have a constraint based on how much mass that we want to retain. And so right now, what we're saying is that through the optimization, we don't want it to eliminate too much mass. So we say that, we at least want to retain half the mass that we started with. So we're going to have a percent to retain of 50%. So changing the setting here will kind of change how aggressive the optimization is going to be. So if you change this to be something higher or something lower first, okay. So let's say that this is 25. So if we set that to 25, then the optimizer will basically be able to take out 75% of the mass in this guy to find an optimized solution. So that's a rather aggressive optimization. Okay? Or we can kind of make this more conservative, where we can say that this is 75. So this will retain 3/4 of the mass here, so it only eliminate 1/4 of it. Okay? So you can kind of play around with this. So actually in the activity, once you're working on this on your own, I want you to kind of play around with this setting and kind of see how that affects the results. Okay. Okay, are there any questions on this? Question? Yes. Oh, yeah. That's right. So yeah, in the objective here, we're reducing elasticity. That's correct. Mhm. Yeah. Thank you. Okay. Okay. So now that we've set all of our settings, we didn't really change all that much. Actually, we didn't change anything. We kind of just left everything on default. But now that we know what all the settings do, we can go ahead and hit solve. So let's go ahead and click solve here. Okay. So it's going to take a while. So grab your popcorn. Okay. But the cool thing about this this optimization is that you can kind of view it in real time. Okay. So after you click solve, what you can do is you can click this plus sign next to solution information, and you can click this topology density tracker. And what you can do is you can see the optimizer take out mass kind of in real time. So right now it's kind of preparing for the optimization, but once it's kind of done that, you'll start to see mass be taken out of this this model. Okay? So visually, it should kind of look like termites are kind of eating your model. So you'll see a lot of kind of rough edges, but you'll see it should kind of eliminate places where it thinks the stress is going to be low. Okay, so you can also track where it's going in the bottom here. Okay. Right. Okay, so you can start to see that it's starting to eliminate the mask. Okay. So it's doing kind of a smart guess and check where it's it's guessing solutions and seeing how much better it is than the other one. Okay. So you can see that it's eliminating this portion in the front right here, because remember that portion right there was dark blue, so it wasn't really doing any load bearing. Okay, and then it's also eliminating this portion in the back right here, which is also doing very little load bearing in itself. Okay? So you can see the optimization is now done. So because we had a fairly coarse mesh, it didn't take us too long. But of course you can change the mesh even more. Okay? Right. And here's our optimized geometry. Okay? So it doesn't look very optimized, right? So if you kind of took this part and you kind of gave it to someone to machine or to manufacture, they're going to call you a crazy person because you have all these kind of really rough edges right here, and there's no way to kind of reasonably do that. Okay, but you can kind of see some characteristics of a more optimized geometry where this kind of frontal portion here is not really doing much in load bearing. So if you go back to your CAD model and kind of subtract this part out right here, so you can kind of save that much in material. Kind of same in the back right here. So in the back, we can see that these areas right here, we're not really doing much load bearing. So we can kind of really do without them. Okay. So you can kind of use these as kind of guidelines to go back to your CAD model and modify. Okay. So I set the maximum to 500 iterations in this case, but it'll probably kick out a lot sooner just because in this case, the optimization was fairly simple. So it's probably not going to reach 500 iterations. So yeah, in this case, it only reached 15. So at 15, it basically the other setting right here, which was the convergence accuracy. So after 15 iterations, it said that our solution is not really improving that much more. So it basically kicked us out of the optimization. So in this case, it kind of reached this threshold way before it reached that. Okay. So for relatively simple optimizations where you only have one objective, this is really usually going to be the case where you get kicked out after so many iterations. But for more complicated ones, it might reach that kind of maximum level there. Yep. Okay. So if you so in this activity was based kind of heavily around a YouTube video tutorial. Okay? So if you look at that tutorial, what you should see is that after performing this optimization, this person actually took this geometry into SpaceClaim and kind of cleaned up the geometry there. So that's certainly one way that you can do it. You can't do it with this one because I created the geometry in Design Modeler, but what I think is kind of for more complicated geometries, which are what you're going to be working on for your projects, and for more practical problems, I think, doing that cleanup manually in space claim, I think would be, way more trouble than it's worth. So I think kind of the smarter way to kind of use these results is to kind of just look at them qualitatively and look at kind of the regions that the optimizer took out. And then what you can do from here is you can, take this information and then open up your CAD software by SolidWorks again, and then, say that this region right here was not that important. So in SolidWorks, you can kind of much more easily kind of cut out these selections right here. Okay? And in the end, you end up with a part that uses a lot less material. So in this case, it uses 25% less. Okay? But you can change this to kind of change the aggressiveness of your optimization. Okay? So for the activity, the first thing I want you to do is I want you to play around with this number a bit. Okay? So we did one at 75, which is a fairly conservative optimization. So let's change this down to 50. Okay? And let's see, what that results in. And so for the activity, what I want you to do is I want you to try 5 different percentages, and then show me kind of the ending screenshots for those, and kind of just kind of discuss kind of what are the differences in between those screenshots. Okay. All right, so we did 75 just now, and then now we're going to look at 50. Okay. So this is the results for 50%. So you can see that kind of the optimizer just kind of cleaves a divide kind of right in the middle of the wall bracket. And so what that tells us is that having one wall bracket with all this kind of wasted material to hold this mass is kind of a waste. So what's kind of more efficient is to just use 2 wall brackets that are much thinner, and then they can kind of hold your mass a lot more easily. Okay. So I want you to play around with that. So change this, do 5 different percentages and show me the ending screenshots for those. Okay. And so the next part of the activity, what I want you to do is try some different loading scenarios. So we did one loading scenario here where the force was going vertically downwards. So I want you to do an optimization where you change the load a little bit, and I want you to see how that affects the optimization. Okay. Right. So if you're taking this class for graduate credit, I want you to kind of do it on a different wall bracket. Okay. So kind of repeat this whole process, and then after that, then you just have to write your summary. So hopefully this is won't take you too long. It's kind of once you kind of set it up, you kind of just let it run in the background a bit. Okay. And with that, that's all I got for this activity. So this is the topology optimization. So it's a pretty cool tool. And you can use it for a lot of different things. Yeah. If you give this part to a machinist, they will they would probably at least laugh at you. Some violence might occur, but it depends on the machinist. So Chris asked the questions, can you do an optimization on kind of multiple physics at the same time? So we did an optimization on static structural, but theoretically it should be possible to do an optimization on a thermal simulation and a structural one at the same time. So you can optimize things for elasticity, but also for like thermal stresses too. I'm guessing that you can, because I think is that you would kind of have to do both a structural and a thermal simulation kind of independently, and then link both of those up to the optimization. And then you'd have to kind of modify your objective to kind of account for both of those things. But I don't see why not. It might be a feature that might be locked in the student version, but I'm sure that it must be there for the commercial one, because that's kind of multi-objective optimization kind of at its finest. Yeah, I'm not sure. I haven't tried it, but I think it's at least worth a try just to see. Because I remember someone said something last time where, like, if you kind of have multiple instances, it kind of takes each instance and kind of adds the total amount to the node count. So if you have kind of a structural and a thermal, basically the maximum amount of elements for each is going to be halved, because the total amount of elements in that case it has to be it adds up to 32,000. Right, so the question is, isn't this usually used for prototyping new designs and then adjusting? Yeah, so certainly this is, I think this is used kind of in the stage kind of before you fabricate it. So, you know, once you're if you're using finite elements to kind of prototype new designs or to trying to develop new designs, this is something that you can kind of factor into your process to kind of, you know, maybe do some improvements that you might not have seen kind of yourself. Right. So some programs have another step that makes this rational for machining and real life development. I think so. Yeah, I haven't really looked. I haven't really seen those kind of stuff, or I don't have experience with those stuff myself. But I'm sure that those exist because, you know, turning this into a machinable part is, you know, not trivial. You need to kind of you know, have a lot of skills in SolidWorks. So I'm sure there are kind of a lot of automatic tools that you can use to kind of smooth this out and kind of you know, make the edges a lot sharper to make it a lot easier to machine. So so SpaceClaim has a little bit of that, but it's a very manual process. But you're right. I think there are some other programs that kind of do it more automatically. I see Fusion 360. I need to check that software out. I've heard that a few times. Yeah. Okay. Yeah, maybe I'll learn from Dr. James one day. All right. Any more questions on this activity? So, you know, we have 15 more minutes. So for now, you know, I'm just answering questions, but, you know, we're ended a bit early today. So on Thursday, what we're going to do is I have another handout there to do a fatigue analysis. So I know for some projects, some people were interested in doing some fatigue testing. So to see, you know, how well their part is going to hold up to kind of multiple load cycles. So we'll go over that on Thursday. So I expect that's going to be a fairly short lecture, so maybe kind of around the same length as today or shorter. And then Tuesday, what we're going to do is we're going to do our CFD tutorial. So that's not an activity, so that's just going to be a handout. So that's just for your guys' information. You know, so I'm still in the middle of working on that, so I should have that ready, you know, by sometime tomorrow probably. And then next Thursday, we're going to have Dr. Sanders come in and kind of talk about his research in finite elements, because he has a much more solid mechanics background than I do. Because my background is mostly fluid mechanics, so, you know, a lot of my research kind of more applies to 417 more than it does to 410. So we kind of did a swap where he asked me to kind of give a talk in his class, and then in exchange he's going to give a talk in my class. So so if you're kind of interested in kind of seeing the research applications for structural finite elements, then that would definitely be a good talk to go to. Yeah. So if not, so, you know, I'll hang around until the end of lecture, but you know, for those of you guys got to go, I'll have a great afternoon, guys. Have a great day, and I'll see you guys on Thursday. Yeah. Yeah, so I have office hours at 5:30 after this. Okay, final project due date. That's a good one. So so before I think I said that the final project was going to be due on the day that we would have our final exam, since we don't have a final exam in this class. But because of, you know, all the craziness that I know you guys are going to be going through the last 2 weeks, I want to give you guys another week to work on it. So I think our final exam was going to be Tuesday of finals week. So I'm going to have it due on the Tuesday after finals week. So I think that's Tuesday, May 19th. Yes. Yeah, so next week, 16th week, next week's finals week, and then Tuesday, May 19th. So the final project will be due Tuesday, May 19th. Yeah. So I need to submit grades on Friday of that week. So I need a few days to grade it, especially because I have another class doing final projects. So that's kind of as far back as I can push it to still kind of give me enough time to grade it. So we'll have it due Tuesday, May 19th.
Hey, Professor, I have a question about my the final project, but
Sure.
so it's just regarding the update that we sent.